In this presentation, I'm going to explain the overflow limit cycle oscillation and scaling. The previous presentations, we were discussed about the zero input limit cycle oscillation. That is, in an IA system, the constant input is expected to give zero output. But due to the quantization of multiplier, the output is oscillate between a fixed range of signals that is called as zero input limit cycle oscillation. In addition to that zero input limit cycle oscillation, that is because of the product term, we have few more oscillations with respect to addition that will change or that will oscillate the output between maximum or minimum amplitude. This oscillation is called as overflow oscillation. For example, consider a number n1 is equal to 0.375. Convert this into binary, that is 0.1011. And I'm choosing one more number 0.75, and that binary representation is 0.110. When I'm adding these two numbers, the result is 100.1. So the actual answer is 1.125. But if suppose if I am selecting finite word length for the input, the result is also similar to the same word length. For example, here I am assuming that inputs are 3 bits, so the output is also considered as 3 bits. So that overflow, the additional bit is actually considered as sign magnitude. So your answer is assumed as minus 0.125. For this case, because of this overflow, the answer, that is output, is oscillate between two numbers because of this finite word length used to store the sum. That is mainly named as overflow limit cycle oscillation. So I'm just showing the characteristics of this overflow limit cycle oscillation. Here I'm just representing the number of input in x-axis, and the addition result, that is function of n, is represented in y-axis. The graphs vary or oscillate between the maxima or minima. So this is the transfer characteristics of this adder. But this can be, this overflow error can be overcome by saturation arithmetic. In the saturation arithmetic, again I'm selecting that number of input is in that x and function, that is addition result, is in y. So here, if there is overflow detector, then the output is set to be an, or it is allowed, or it is set to be a maximum allowable value. If that overflow is detected, then the output is set to be a maximum allowable value. If the underflow is detected, the output is set to be a minimum allowable value. If the overflow is detected, the output is set to be a maximum allowable value. If that underflow is detected, that output is set to be a minimum allowable value. So actually this is used for eliminating that limit cycle due to overflow, but it causes undesirable signal distortion. So in order to limit the amount of nonlinear distortion, it is important to scale the input. For that, I am going to select one second order IIR filter. So I am just representing the filter equation here. First, I am going to draw the filter. So I just selected on IR system. So input I am giving the name as X of Z, output is Y of Z, and intermediate stage answer is W of Z. Now to avoid that overflow, I am introducing the term scaling factor. I am going to multiply the scaling factor in the beginning of this input. That is, it is introduced between the input and first adder. So first, to identify the scaling value or scaling factor, I am going to simplify this IR filter function. For that, first I am representing the filter equation H of Z, that is equal to y of z by x of z, that is b1 plus b2 z inverse plus b3 z power minus 2 divided by 1 plus a1 z inverse plus a2 z power minus 2, and this is multiplied with the scaling value s naught. Now I can say this h of z is equal to s naught into numerator with respect to z and denominator with respect to z. So this is a general representation for this IAR second order filter. Now I am just choosing that first half because the scaling is directly involved with the first function, that is first terms. So here the output is W of Z and input is X of Z, that can be related with the intermediate transfer function H dash of Z. So I am just representing H dash of Z is equal to W of Z divided by X of Z. So if I'm representing the equation for this one, I'll get this term as S naught divided by 1 plus A1 Z inverse plus A2 Z power minus 2. Now I can represent this as S naught divided by, it is similar to D of Z. So this is the term we got it for W of Z by X of Z. Now for identifying that intermediate answer W of Z, I'm doing the cross multiplication. S naught X of Z divided by D of Z. Just for the simplification purpose, I'm going to choose this 1 by D of Z is equal to S of Z. So now W of Z is equal to S naught X of Z into S of Z. So now to identify the scaling factor, first I'm going to calculate the time domain representation for this given representation. For that I am choosing inverse Fourier transform. So W of n is equal to 1 by 2 pi integral S naught, and I'm just replacing the z by e power j theta in s of e power j theta into e power j theta n d theta. So now, just for the simplification purpose, I'm taking square, that is S naught square divided by 4 pi square integral x of e power j theta into s of e power j theta into e power j theta and d theta the whole square. Now for this equation, I'm going to use Squart's inequality, that is W square of n is less than or equal to S naught square into 1 by 2 pi integral modulus of x of e power j theta the whole square d theta into 1 by 2 pi integral s of e power j theta the whole square d theta. So now W square of n is less than or equal to S naught square, and this term is equal to Parseval's identity, that is summation n is equal to 0 to infinity x square of n. And I'm going to keep the second term as it is 1 by 2 pi integral S of e power j theta the whole square d theta. And we know that in the beginning we selected e power j theta as z, and from this d z is equal to j e power j theta into d theta. From that d theta is equal to d z by j into e power j theta, that is equal to d z by j into z. So now I'm going to apply this in the previous equation. So w square of n less than or equal to s naught square summation n is equal to 0 to infinity x square of n into 1 by 2 pi integral S of Z. Since it is an inverse Z transform, we are going to select the circular integration because Z plane is a circular plane. The whole square dZ by JZ. So now this W square of n is less than or equal to S naught square. Summation n is equal to 0 to infinity x square of n into 1 by 2 pi. I'm just choosing the j's outside. Circular integration, I'm just representing this as S of Z inverse into Z inverse dZ. Since modulus I selected S of Z into Z inverse, and this new denominator Z is taken to the numerator, so we have got Z inverse. So now we know that this W square of n is actually less than or equal to summation n is equal to 0 to infinity x square of n. That is the output is either equal to the input or less than or equal to the input. So for the second order IR filter, so to satisfy this representation, we are going to substitute the remaining term. That is 1 by 2 pi j circular integration S of Z inverse into Z inverse dZ equal to 1. So from this, the scaling factor is equal to 1 divided by 1 by 2 pi j circular integration of S of Z inverse into Z inverse dZ. Now From this, I can say this is equal to 1 by 2 pi j circular integration. In the beginning, that d of z 1 by, that is only replaced as s of z. So I'm replacing it here. So 1 by d of z, that is denominator of z inverse into z inverse dz. So from this we can identify the scale factor. So now the formula for identifying the scaling factor is 1 by I, where this I is equal to 1 by 2 pi j circular integration 1 by d of z inverse into z inverse dz. Or I can say this is I is equal to residue of 1 by d of z inverse into z inverse. So with the help of this I, we can find that scaling factor. So I hope you are clear with that. Thank you.